Good morning and welcome. I'm Mike McFadden, President of the American Geophysical Union. From the deepest depths of the ocean to the furthest reaches of space, AGU members do research that inspires wonder in people all over the planet and that addresses many of the great challenges we face as a society. The Fall AGU meeting is a showcase for much of this groundbreaking research, and there are exciting stories for us to tell to the world. I'd like to welcome the 150 or so reporters and bloggers who have come to San Francisco to find these stories and to write about them. This year, we are offering more than 20 press conferences to provide journalists with accurate and in-depth information about newsworthy AGU science. So let's start today with a remarkable saga, that of the Mars rover Curiosity. After hurtling through space for 8.5 months, Curiosity made a precision landing on the floor of Gale Crater last August, reigniting the public's love affair with space exploration and discovery. For the scientific community, this astounding achievement has inspired a similar surge of enthusiasm. While the rover has yet 18 more months in its primary mission, today's speakers will share with us some of the early findings of Curiosity's travels. It is my pleasure to introduce the first of our panelists, Michael Meyer, program scientist from the Mars Science Laboratory at NASA headquarters in Washington, D.C. Michael?
Well, thank you very much, Mike. On August 6th, the Mars Science Laboratory landed Curiosity in Gale Crater, and its purpose is to explore and determine whether or not that region was ever able to support life. Well, we actually picked the right place because we landed right on an ancient riverbed. So this has already checked one of the boxes in terms of whether or not this place had signs of water, at least in its past. Let me show the first graphic. Oh, okay, there we go. So just to give you some orientation of where we landed and where we are and where we're going, Bradbury Landing is the landing site, and you see kind of a bluish tinge to the area. That shows the scours from the retro rockets as it was placing the rover down on the surface. And over the course of multiple sols, Martian days, we moved to an area called Rock Nest, and we spent a fair amount of time exploring there, looking at the rocks in the area and then also the sand and dust, in which we're going to talk about today. And we've kind of completed that campaign and have moved to Point Lake, where we've done some panoramas in preparation of moving into Yellowknife Bay so that we can do an extended campaign there before then we reach the long-term goal of heading toward the layers in Mount Sharp. So the Curiosity rover is kind of like a CSI laboratory on wheels. It is fully functional with exceptional capability, and all the instruments are performing exceptionally well. We have completed the first soil analysis of the sand at Rock Nest, culminating in measurements by SAM, which is the gas chromatograph and mass spectrometer on board. These results are an unprecedented look at the chemical diversity in the area that is representative of the rest of the planet and forms a solid baseline for our continued exploration. In this press conference, the panel will discuss the results from these analyses at Rock Nest. So let me take this opportunity to introduce the panel. On my immediate left is Ken Edgett, who's the principal investigator of MAHLI, which is the Mars Analysis Hand Lens, Mars Hand Lens Imager, and he's at the Maryland Space Sciences System in San Diego, California. Next is Ralph Gellert, who is the principal investigator of APXS, which is the alpha particle X-ray spectrometer, and he's at the University of Guelph in Guelph, Ontario. Next to him, further to my left, is Paul Mahaffy, and he's the principal investigator of SAM, which is the sample analysis at Mars, and he's at the Goddard Space Flight Center in Greenbelt, Maryland. And then at the far left is John Grotzinger, who's the project scientist for Curiosity, and he's at Caltech in Pasadena, California. With our fully functional Curiosity, we begin 2 years of exploration, our near-term goal, the exploration of Yellowknife Bay, and then onto the sedimentary layers of Mount Sharp in the coming year. To explain further and give us an orientation of Rocknest and to talk about his instrument, I turn the mic over to Ken Edgett.
All right, thank you. Well, I've got a graphic here. This is our rover Curiosity. This is a mosaic of images taken by the Mars hand lens imager out on the end of Curiosity's arm. And so you actually can't see the arm because it's sort of out of view of the camera. This is our rover parked at the place we called the Rocknest wind drift, which is the feature that we've been scooping and that these guys are all going to talk about this morning. We scooped this thing. We parked here for about 6 weeks. We scooped it 5 times. You only see 4 scoops there, and then you see I've drawn one in blue there called Scoop 5. That's the one we did after we took this mosaic. Scoop 5 is the one that the SAM, which Paul will talk about, analyzed. And that little drift is only about 4.5, 5 inches high in the area that we were scooping. I've got some more pictures because that's what I do. Here are 2 of the scoops, number 3 and number 4. 3 is the one on the left there. So you're seeing not quite a closest resolution you can get out of this camera, but you're getting a view down into these scoops. And what you see is that the bulk sand that's down inside this drift was a sort of fine, very fine sand. It's very dry-looking stuff, just like you'd expect. And this was important. This is what we were looking for to process through our sample handling system to first clean it out and then to deliver the fine sand samples to the mineralogy experiment as well as the geochemistry experiment. And the surface of this drift, oh, by the way, so that sand, that fine sand, the grain size is sort of like these artificial sweeteners, okay, in terms of size. So it's finer than sugar, but coarser than something like flour. Then the surface of the drift was covered with coarser sand, more like the size of the salt grains on those big hot pretzels you can get. So they're like a millimeter or so in size. Y'all hungry yet? And and then coating those coarse grains was a dusting of actual Mars dust, and that sort of gives the surface surrounding the scoops a lighter color than the sand that's down inside the ripple itself, or the drift itself. The dust coating and the fact that there's actually little clods in there, so tell us the upper few millimeters or the less than half an inch was also a little bit crusted. All of that, I'm getting hungry. All of that tells us that this drift is actually inactive at the time we scooped it. It had been sitting here for some period of time. We don't know how long, but it had been there for a little while. And then the Mars hand lens imager, its specialty is not just mosaic of the whole rover, but we can actually get down and dirty, get down close to the sand and get close-up views in color. On the left side of the screen, you see a slide that emphasizes the coarser sand. This is the stuff that was on the surface of the drift. And then on the right side, you see the very fine sand that was from down inside the scoop. And it's sitting, in this picture, it's sitting on an observation tray that's made out of titanium. That's that gray background. This is a tray for the Mars hand lens imager, and the APXS, which Ralph will talk about, to view sand on an unnatural surface, on a surface that allows us to see a fraction of the same sample that's being delivered to the mineralogy and geochemistry experiments. And of course, we see a tremendous variety of colors and shapes and crystals. There's pieces of mineral crystals and stuff in there. So it's a really rich place to go take our first look at something that we can scoop and ingest into our analytical instruments. I'm going to pass it to Ralph, and he's going to talk about the composition of this drift.
Yeah, thanks, Ken. We wanted to make actually sure that this is not a very special soil sample. It should be an ordinary Martian sand soil. I show you in the very first slide here various soils that we measured in previous missions. On the lower right, it's actually the spot that we measured with the APXS for chemistry in the wheel scuff. And all the reddish surface soils here look chemically very similar, beginning with the Viking mission on the left, lower left. We did not want to actually have a too unusual soil for the first sample like the ones you see on the top. These are subsurface soils that the Rover Spirit encountered in Gale Crater. These showed heavy alteration. We will be delighted if we find something in the surrounding here later on, but we wanted to have a usual soil, and that's what we found. We made measurements in the scuff. We made measurements also with the size fraction that is delivered to the analytical instruments, and we compared both of these soil sample chemical results, and they are identical. We also made measurements on top of the wind drift. We couldn't measure too many soil samples with the APXS, which is mounted on the arm. We couldn't actually measure the empty scoop hole. This was checked with the laser ChemCam instrument. Everything looked very homogeneous. And that's not a surprise. If you look at the compositional differences between the Meyer chemistry of the soils in red and green to the result we got in the scoop, in the scuff, they are very similar. And the black bars are the variation that we found on Meyer during the traverse. So this is the average over up to 50 soils. So all this is the typical ordinary Martian soil that we wanted to have. And what you see in this chemical makeup is from the very beginning mission in Viking, it was known that there are 7, 8, up to 10% volatiles in there, sulfur and chlorine, so elements that can form salts and are volatile. They were not well constrained, and we were looking forward to actually see what SAM does out of this. Also, we cannot measure carbon with X-ray spectroscopy. So with this, I hand it over to Paul to tell us about the findings of SAM.
Yep, great. Thanks a lot, Ralph. Yeah, we really consider this a terrific milestone. The two instruments buried deep inside Curiosity get their first gulp of Mars material, first gulp of solid sample. We had sampled the atmosphere before. And this may look like just a dusty sand pile, but Sam and Kemen must have found this pretty appetizing because they went back for more portions. We've now analyzed 3 portions with Sam, for example. It really is a rich data set. The Kemen XRD, which was reported on, X-ray diffraction, which was reported on some weeks ago, is really the very first time that this type of experiment has been carried out on Mars. It really broadens the breadth of the identification of minerals that we can find. And with SAM, it's really measuring evolved gases with a combination of techniques that have not yet been carried out on Mars. So what I'm going to do is talk a little bit about the highlights of the SAM data, the volatiles, the gases released from these samples. But let me start off by saying SAM has no definitive detection to report of organic compounds with these first set of experiments. And you may find that statement a little curious because a little bit later what I'll show is some organic compounds that we identified with the gas chromatograph mass spectrometer, and we were on Mars. And so wait a few minutes and we'll talk about that in a little bit more depth. It's not unexpected necessarily that this sand pile would not be rich in organics. It's been exposed to the harsh Martian environment, and we really selected that site in order to scrub out the sample processing system. We flushed it really, shook this sand around, and then deposited it back on the surface to really try and remove any surface organics from the sample processing chain. So let me explain a little bit with this first graphic how we got our first sample. Instead of just opening valves and letting some of the atmosphere in, what we did was we accepted a portion of sample from this scooped sample that had gone through a sieve, and then a little trap door opened, and a cover to SAM opened. We have a little funnel there that we vibrated, and sample went down into a quartz cup. And the sample manipulation system, you can see in the upper left of the graphic, it really has 59 quartz cups in there. And for each sample, we used one of the cups. The cup then moves the sample into an oven, and then we start heating up the sample and analyze it with 3 experiments. And the neat thing about the way we can capture gases as they're released from the sample is we can either analyze the gases directly as they're being released from the sample with the mass spectrometer. We do that with every experiment. And then we can select a portion of the gas to detect either to the tunable laser spectrometer, where we look for isotopes, heavy versus light elements that are contained in the sample. This is really important from trying to understand the changes in the atmosphere with time. Light isotopes tend to be lost heavier over geological time from the atmosphere, especially at Mars, than heavy isotopes. Or we move a little stream of that gas into a trap that will later be used to analyze the sample for organics. So the 3 instruments are shown there, and the little hydrocarbon trap that we are trapping organics. If you take a look at the next graph, this really in the chart here is a plot of the major gases that were evolved from the sample versus sample temperature, all the way from ambient to above 800 degrees centigrade. And you can see those bars on the bottom. The red and blue bars are respectively where we direct that bit of gas into the tunable laser spectrometer and where we direct the gas past that hydrocarbon trap for analysis of organics. So those 3 sets of bars really represent 3 experiments. And look at the gases that are produced. Water was a major gas. It's interesting. That was several percent. We'll talk on the next graph about the deuterium to hydrogen ratio in that water. The next most abundant gas is carbon dioxide. The high temperature part of that potentially could be from an iron or magnesium carbonate. That's really interesting. And so if you look at the red bar below that, we sent a little bit of that gas to the tunable laser spectrometer, and we can analyze the isotopic composition of the CO2 that's released with the TLS. And then the lower temperature gases there were trapped for later organic analysis. The other gases that I'm showing on the chart are oxygen vapor and SO2, and we'll talk about those in a little bit. And so this next graphic that you see up on the screen is really representing the deuterium to hydrogen ratio. It turns out that if you take some ocean water, maybe some of the water that's in the San Francisco Bay, 1 in every 6,420 atoms is the heavy deuterium atom. That's the standard mean ocean water deuterium to hydrogen ratio. And what we've plotted here in this graph is really the ratio of relative to Earth of what we're finding in the gases released from the soil. And it's more than 5 times the ratio of deuterium to hydrogen in this gas released from rock nest soil. And that's just really terrifically interesting. We can try and get those measurements spectroscopically from Earth, and there have been very good measurements done. But the issue is that there's a seasonal change both in the water abundance, and you can see that in the bottom chart, where orbital data has shown the reds are the high water, the blues are the low water, and here you're looking over 2 Mars seasons. And with the abundance of water in the atmosphere, and that's kind of these lines on the upper left chart that are showing that there's a seasonal change in the deuterium to hydrogen. So as the mission goes along, we're really trying to get what might be the average deuterium to hydrogen ratio to really tie back to, over time, how much water, how much hydrogen from water has escaped from the atmosphere. And that's what that's trying to tell us about early Mars climate, for example. And so this is just a start, but we got one really interesting measurement here of deuterium to hydrogen. And that's a really interesting result from our point of view. The next slide shows the evolved oxygen in the blue and sulfur dioxide in the red. What we're really plotting here are individual mass to charge signals from the mass spectrometer. We scan from 2 AMU all the way to 535 atomic mass units. So we have more than 500 of these traces going across the temperature of the mass spectrometer. And here we're just plotting a couple of them, three of them actually, to illustrate our point. So with water, the blue we're seeing, with oxygen, the blue we're seeing oxygen and then its isotope. But then over to the higher temperatures, what we're seeing in mass 34 there is a little bit of hydrogen sulfide, which is really interesting because the major evolved gas is sulfur dioxide. So this sample is pretty oxidizing, but there's also some reduced hydrogen sulfide there. And the oxygen is really interesting because it looks like it potentially could come from a compound such as a perchlorate. The one that we're looking at right now, we still have to confirm this with laboratory experiments, is calcium perchlorate. And when that breaks up, it releases both chlorine and oxygen. And the release of oxygen is shown here. The release of chlorine really ties to what I'm going to show on the final slide here, which are these very simple chlorinated hydrocarbons that we see. 1-chloro, 2-chloro, and trichloromethane, and then an unidentified heavier chlorinated compound. We're working on that. And the reason we say we don't have any, even these are clearly there, we clearly detected them. The reason we're saying we have no definitive detection yet of Martian organics is that we have to be very careful to make sure both the carbon and the chlorine are coming from Mars, for example. We have to make sure that the carbon is not coming from any residual terrestrial carbon that we have in our system. The carbon, for example, could also come from inorganic carbon, the CO2 that you saw released on the earlier graphic. And as the perchlorate breaks up, it might produce, for example, hydrochloric acid that reacts with some of the carbon and forms these compounds. So there's more work to do, but it's a really interesting study to pursue. We'll hopefully get back to other materials like this as the mission goes along. And just one final point, that in this very exposed material that is exposed to the harsh environment of Mars, there are many processes that could destroy even the organic material that we expect falls in from space. Cosmic radiation over time, over hundreds of millions of years, can destroy organics. We know there's hydrogen peroxide in the atmosphere. It can destroy organics. Ultraviolet radiation can destroy organics. So it's really going to be an exciting hunt, I would say, over the course of this mission to find early environments that might be kind of protected from this harsh surface Mars environment and really see what we can add to the hydrocarbon, the organic story. In the meantime, as you can see, we have lots of other things to look at, a whole suite of isotopes, and we'll be looking for these in different environments on Mars. So without going any further, I'll pass it over to John.
Thanks, Paul. Okay, so I just want to reiterate something that Paul just concluded with, is that the instrument, SAM, is working perfectly well. It has made this detection of organic compounds, simple organic compounds. We just simply don't know if they're indigenous to Mars or not. And so, it's going to take us some time to work through that. I know that there's a lot of interest in that. And but the point is that Curiosity's middle name is patience. And we all have to have a healthy dose of that. And the reason why is I'm going to come back to our soil for a minute and try to give an example of that. As Paul mentioned, we basically took this material on and we had to do a lot of work to make sure that this was something that was sort of the garden variety typical Martian soil. We didn't want something that was adventurous because if we thought that was the case, based on our preliminary assessment using the APXS and the ChemCam instrument, if we thought we had something that was chemically going to be very difficult to work with, we probably would not have immediately put it into the machine. And instead, we went through a very long set of triage experiments to make sure that this material would not undergo a state change and maybe evolve water or something while it was in the rover. So we were very, very careful, and this took actually about a week or 10 days to work through before we could actually even do the first analysis. Now, being hopeful then that there was no gunk that we were passing into the rover, we went ahead with the next step. And what is interesting is that if there's one sort of if I can try to capture everything you've just heard here as simply as possible, what we've got is a globally representative material on Mars that turns out to also be a rich repository of environmental process and history. And that is basically what we're trying to do with this mission as we go about assessing habitable environments. The soil has been our sort of practicing or proving ground for what we've got. And we took something that we thought was a relatively average material, and as my colleagues have shown you, we've learned a whole lot more about it than we knew before. It is also the first fully integrated measurement for the mission in which virtually every instrument was involved in contributing towards the success of this operation. APXS and ChemCam gave us the chemistry. ChemMin gave us the definitive mineralogy, and if you go to Dave Plake's presentation this afternoon, he'll point out that there's a significant portion of this which is X-ray amorphous that Paul's SAM instrument was then able to tease apart as he just described. SAM, in addition, gives you sort of a global insight, really, into this material, which is distributed. Everybody's heard of global dust storms. Now we're actually analyzing the material. And what we learn here, what we measure locally, is actually applied regionally and globally in terms of what insight we get from that. The DAN instrument gives you a broader sense of the distribution of hydrogen or neutron-absorbing materials in the subsurface that helps flesh out the story. The science cameras, as Ken showed you, gives us the physical structure of the soil. REMS, the weather station, turns out to have been very important because we learned from the Phoenix mission that when we drop off samples, if the wind is blowing, it may just blow your sample away. So what we do is we sample the wind velocity profile over 24 hours, multiple times, to see that time of day when we have the best chance to just have the sample drop right in to the instrument, and that was 100% successful in every run that we did. And then finally, RAD, which is the instrument that gives you the radiation flux. As scientists get interested in understanding the inventory of organics that fall in from space or any other organics that are indigenous to the planet, radiation is one of the principal ways. It's a destruction pathway that takes those organics and reduces them to simpler materials, maybe ultimately even to liberate them to form carbon dioxide that we would never detect as an organic compound. Now, the important thing about that is that for the first time we have measurements of the radiation flux right at the place where we were sampling the soil. So you're going to expect to see a whole new generation of modeling studies, I think, start up from that. Okay, so now I want to move on to a somewhat different subject that we call our 3 months of terror. Everybody's seen that blue shirt moment where everybody was jumping up and down, celebrating the successful EDL system. Ours really isn't so much 3 months of terror as it is 3 months of tension. Every day we turn on an instrument. We do the electrical baseline check. It looks like it's going to work, but you don't really know what it's going to work until it's actually done a measurement. And then once you've done the measurement, you wonder how well it's done compared to all the calibration and baseline testing that you've done before you launch the spacecraft. And so each day we go through that, and as we turn these on, as one of our team members from Texas decided to call them, we have a hootin' and hollerin' moment. And everybody's jumping up and down in the science team, and we get all excited about that. But in the end, what basically happens, and with the SAM instrument in particular, SAM just comes last. It's at the end of the sample processing chain. It's also an extremely complicated instrument. It's practically its own mission. And when it works for the first time, we have a hootin' and hollerin' moment. But when it works for the second time, you get something that all scientists live by, which is a repeat analysis. You see that what you saw the first time is probably not going to go away. And then when you do the third sample, and the configuration is pretty much the same it was the first time, you believe maybe this just might be one for the history books, that this is going to stand the time of test as a legitimate analysis on the surface of Mars. That's basically where we were at with that excitement by the science team. So the nature of scientific discovery, especially in this business, is also very important. We live by multiple working hypotheses. As Paul mentioned, even though his instrument detected organic compounds, first of all, we have to demonstrate that they're indigenous to Mars. Then after that, we can engage in the question about whether they represent the background fall of cosmic materials that are organic in composition that fall on the surface of every terrestrial planet. And then after that, we can begin into the more complex questions of whether or not this might be some type of a biological material. But that's well down the road for us to get to. And finally, serendipity. As any of us that have worked on the Earth understand, on a planet that's teeming with life, you can go out into rocks that are billions of years old, and the probability of finding something that is actually a sign of life, or even something as simple as an organic material, those discoveries are so rare that every time we find one, it makes it into science and nature. Every new discovery, new occurrence, is actually a major discovery. So we have to take our time, and it's going to take a bit of luck, but it is serendipity because we're going to think it through well ahead of time and go about this exploration in the most intelligent way that we can, using all of our instruments. What this mission about is integrated science. There's not going to be one single moment where we all stand up and on the basis of a single measurement have a hallelujah moment. What it's going to take is everything that you heard by my colleagues and all the other PIs that build all their instruments. We're going to pull it all together, and we're going to take our time, and then after that, if we found something significant, we'll be happy to report that. So finally, then, where are we headed? Well, at this point, basically, our car is ready to go. This is a car that comes with a 10,000-page user manual that we also have to write as we read it. And, that's where the patience comes in. But we're getting closer. We're ready to go here now. We have one major test ahead of us, which is the drilling. And we hope to do that and get started on that before the holidays begin. And then sometime early next year, we're going to pack it up and start driving towards Mount Sharp, which is the reason we picked this site. And it has what from orbit look like a lot of materials that we're interested in. So we're going to load up the car with the science team. We've been at the gas station. We've gassed it up, checked the oil. We're going to kick the tires around a little bit, but then we're ready for our trip, and that's when our science mission of exploration really gets into full gear. So thanks, everybody, for listening.
Thank you, panel. My name's Peter Weiss. I'm the Public Information Manager of AGU, and I want to reiterate the welcome that AGU President Michael McFadden gave earlier. Now's the time for us to have some questions from the press here in the room, and we're also going to be taking questions from the internet that will come through over there from Kate Ramsayer. First, I want to just say that we ask that only members of the press ask questions. And when you do, please say your name and your affiliation. And I just wanted to also mention that at 1:40 today, there'll be a scientific session. It's U13A, and about this mission. And at that session, as usual, meeting attendees will have the opportunity to also ask questions. We're going to take questions for about half an hour, so we'll be ending around 10, and we'll be mixing up questions, like I said, between here on the floor and from the internet. So we're ready.
Hi, I'm Alex Witzy with Science News for Dr. Grotzinger. Can you just take us through how you go about figuring out whether these organics are indigenous to Mars or not? With some gory chemistry detail.
I'll pass that one to Paul, but let me just first reiterate the sort of the high-level approach before Paul gets into the more details of the chemistry. So you make a measurement, and what we know is that the instrument is performing perfectly well. It's very, very sensitive, so that we know the instrument has detected simple organic molecules. Then after that, you have to do a series of tests to verify that the organics that you've measured have not come from Earth, and there are a number of ways that we could bring them with us. Remember, the reason we chose the soil is to try to clean out all that hardware, and we clean it as best as we can on Earth, but there's no guarantees, and so we pass soil through it, shake it around, and then dump it out. Take another gulp of soil, shake it around, dump it out. We try to get it as clean as we can, but it could be riding along with the hardware. And then within the instrument itself, there's always a little bit of stuff that comes along. Every instrument that we make on Earth, even the most sensitive instruments, carry materials along with them that you have to work through and understand their properties. And then after that, if we believe that it's indigenous to Mars, then we have to go through a second level of triage, which is to say, okay, it's on Mars, but maybe it didn't come from Mars. It could be a material that comes from the cosmos, a lot of primordial material. As we know, there's carbonaceous chondrites that in some cases have quite complex organic molecules in them. And then after that, then you begin by the context. And this is where the other instruments really come in and are so important, because they're the things that allow us to establish that maybe this isn't something that actually came from space, but this was actually something that formed in the environment, where the particles that make up the rock, where they were also accumulating, this was something that was being formed at the same time. And then you have a pathway to decide whether or not those formation pathways are abiotic or maybe in the end biologic. And so there's, as you can see, it's a complicated decision pathway there, and we have to explore each one systematically. But I'll turn it over to Paul.
Yeah, I mean, we've gone to great care with this mission to address the potential confusion that might be caused by terrestrial contamination. The materials that we brought to Mars with us, we've done a lot of analysis to understand what kind of gases they release that we might see. We have what we call an organic check material. It's a very pure vitreous silica glass, and we have that doped with 4 very distinctive fluorocarbons. And so if we're looking for terrestrial stuff, not just inside of SAM, but stuff that might come from the sample processing chain, what we can do in the end to avoid confusion is we can drill into one of those 5 organic check materials, run that sample through, and really treat that as a blank. And if we see the same stuff that we saw that we thought might be from Mars, from either some drilled rock or from soil, then we got to say, hold the show a minute, this might be terrestrial stuff. We do even more routinely, we run blanks on internal to SAM. For every experiment that we did here, we ran essentially a blank beforehand, and look, there's very trace residual amounts, for example, of our derivatization agent. Very little bit of vapor shows up. We'd seen some of this as we calibrated the instrument and so on. That's actually great because it shows us that the chromatography is working beautifully. But then if we see that when we have a solid sample in our cup, we go back to the blank and we said, oh, did we see that compound? And if the answer is yes, then it's not from Mars. So we'll do all of those things, but what really helps also is a great flexibility of, you saw those bars, we can select different slices of evolved compounds to analyze with chromatography. We can have different temperature sequences on the sample to release organics. And so all those things combine really to get a story on whether, give us confidence of what we're seeing is from Mars or not from Mars. So that work is ongoing.
Emily Lochtawala from the Planetary Society. This question is for Paul. I'm wondering how many of the compounds that you've identified so far are ones that would be present as those compounds in the soil, or if they're all evolved from other compounds that are in the soil. I'm particularly interested in the chlorine compounds and the hydrogen sulfide.
Yeah, the question really relates to whether the compounds that we were showing might exist in the soil or whether they might be made as we do our experiment. It's certainly very possible that they're, in fact, I would suggest very likely that they are made. As we heat the sample up, the simple chloro single carbon compounds are being released at the temperature that this oxygen signal is coming up, potentially a calcium perchlorate. And so with the high temperatures and chlorine being released, perhaps hydrogen chloride being released, it's very reactive, and then it latches on to whatever carbon is there and forms these very simple compounds. So it's very, very possible, I'd say even likely, that those compounds were not existing, and we really made them as part of our experiment.
Okay.
Hi, Peter Aldous with New Scientist magazine. I wondered if you could address the sort of broader significance of a couple of the results you're talking about. I guess what it means for the evolution of Mars and so on. Of firstly the high deuterium to hydrogen ratio, and the secondly that if it's confirmed that what you're looking at is the breakdown of perchlorates, what that means. I guess given that I think we've already had perchlorates discovered in the polar regions by Phoenix back in 2008, what it would mean if they're indeed here in these more equatorial type regions as well.
Shall I take a start? Yeah, I think that what we didn't report on today, what we've reported on earlier with the atmospheric measurements, was the isotope ratios in carbon and hydrogen in CO2 that the tunable laser spectrometer measured. And those are really very interesting. They're both somewhat about 5% or a little bit less heavier than we would expect from terrestrial CO2, from what we think might be more the solar system average. So the heavy carbon, the heavy hydrogen, the heavy D2H, we're in the process of looking at nitrogen isotopes, which we also will expect will be heavy based on Viking results. So all of those types of things point toward lighter species escaping to space and leaving behind the heavier species. And there are physical processes that can go in the other direction as well. For example, if you had early global oceans on Mars and were to form a lot of carbonates like we did on the Earth, the cliffs of Dover and that type of thing, then that pushes the isotopic fractionation in the other direction. So with some of these isotopes, such as the noble gases, they stay in the atmosphere. It's a pretty clean signature. With other gases, there are two things pulling at the isotope ratios. One is lost to space, and the other is lost to surface capture chemically. And so the combination of all these isotopes, I think, in the end, is going to help us understand the processes that may have stripped an early atmosphere away from Mars. And the whole picture, I think, will be completed later in the program when the MAVEN mission, which is the next Mars launch opportunity, is going to orbit Mars and really look at current escape rates from the planet. And those escape rates that we measure extrapolated back in time with a different activity of the sun, and then those combined with the atmospheric measurements that we're making, and then hopefully combined with what we might find in very ancient rocks, let's say 3.5 billion years ago when Gale Crater might have been formed and a lot more water might have been at Gale Crater. All those things might help us make a model of what the early environment on the planet was. And was this environment conducive to life? Was there water standing around for long periods of time, for example? So the isotopes are really one important way of getting at that question. Perchlorates is interesting that if we have found them, we're still working hard to do some lab experiments that'll try and pin that down a bit. But it's certainly oxygen and chlorine-containing compounds. Whether it's precisely calcium perchlorate or not, we have to study that further. But that might have been formed by atmospheric processes, perhaps when volcanic gases were released. Maybe those materials were formed. And if they're distributed all over the planet, then they kind of participate in the very near surface chemistry. So are we going to find those in very old materials or not? That'll be something we'll be looking forward to as we go along.
Let me just elaborate a little bit more on that to stress one thing. Again, what Dave Blake will talk about this afternoon is that with the ChemIn instrument, we see very definitively the mineral structure that makes up the soil. What we've analyzed here is the fraction that's less than 150 microns that has a very substantial component of it that represents the X-ray amorphous fraction. And so in comparison to the past, some of you will have heard of something called nanophase iron oxide. So this is not a well-crystalline material that wouldn't show up. And basically what the SAM data is beginning to show that there could be all kinds of other species in there as well. Carbon-bearing species, sulfur-bearing species that are not well-crystalline, that are not the kinds of things that you see with the conventional techniques that we use from orbit. And, it's a mixture of mostly oxidized material, but there's also some things in there that could be reduced species. And so by characterizing the chemistry, and as Paul says, especially the isotope composition, we're beginning to get a better handle on how to go about this. At the end of the day, we're talking about habitability and preservation of materials like organics, and deciphering the composition of this material is very important for that. One last thing to underscore is that you will have heard us talk about the strata at Mount Sharp and reading that story there. This baseline of what we see on the modern planet then gives us exactly a frame of reference to go about looking at the strata that might be billions of years older, that tells us about the early environmental evolution of the planet.
Okay, we'll take our next question from the internet.
This question is from Joe Palca of NPR. Do we think that the chlorine in the chlorinated methane compounds came from the perchlorate salts that reacted when the sample was heated?
That's certainly every indication that that's so. We look at our curves of, well, I didn't show the traces that we saw in the direct evolved gas analysis. I just showed the major species that evolved. But the trace amounts of chlorinated species are produced right at that point in time. And where we really nail their identification is with the gas chromatograph mass spectrometer. So they're there, they come up at the same time that this chlorine-containing species is breaking up. So it's every expectation that it came from a perchlorate-like compound.
Hi, Rob Reynolds from Al Jazeera English. For sort of a worldwide, non-specialist, layman audience, I wonder if you could address maybe a couple of things. First, what do you think is the most important discovery or most unexpected thing that you've found thus far on the mission? And secondly, if you could address the, as you know, there was a lot of flurry of expectation and some would call hype about a terrific discovery having been made, and everyone around the world got very excited about that. What does that sort of say to you about the level of interest that people have, non-specialists have, for Curiosity's mission? Thanks.
I'll take that one. With regard to the last part about it is, I think certainly what I've learned from this is that, you have to be careful about what you say and even more careful about how you say it. We're doing science at the speed of science. We live in a world that's sort of at the pace of Instagrams. And, the enthusiasm that we had, that I had, that our whole team has about what's going on here, I think was just misunderstood. And there's not much more to say than that. And I'll just reiterate, in terms of things that we think are great discoveries that the general audience is going to be interested in, our bottom line is that we have a globally representative material that we have analyzed and done it comprehensively with all the instruments. And these comprehensive, fully integrated investigations are going to be the basis by which we make major discoveries of public interest, but we're just going to have to be patient.
And let me answer the first part. I really do think that the major discovery made so far is, in fact, that we landed on an ancient riverbed, flowing water on the surface of Mars. I think that's spectacular.
Randy Shostak, reporter with EOS over at the American Geophysical Union. Just in follow-up to that question, Dr. Grotzinger, I wonder if you could just tell a little bit more about your reaction to how your earlier comment about it's one for history books was taken, both in the media and in the general public, and what your immediate concerns perhaps were.
I was surprised, and the first thing I thought was, gosh, I have to be careful about what I say. The great thing about it is, as the days went by and I thought about it further, my reaction was, I think it's terrific that this mission has such wide appeal and public interest. That's everything that I think we're hoping for. the mission has delivered an unbelievable wealth of data. We've had over 11,000 images returned that the public has enjoyed. We've had over 2,500,000 observations by the weather station. I could go on and on. You know, it's been spectacular. But I want to come back to the point I said before, is that when you see SAM operate as the culmination of everything we do as an integrated mission, and you see the first run come in, you get really excited about that. But what you're worried about is, will it do it again when you give it the second sample? And then when you get the second sample, you begin to think, now we're really doing science, and this team is going to have stuff to chew on for months and years to come. And it's just not much more complicated than that.
Elizabeth Wilson, Chemical and Engineering News. Back to the simple organics. If you do determine that the carbon in these compounds is indigenous to Mars, how do you go about telling if it's biologic or abiotic? I mean, would you be looking at carbon isotope ratios or things like that?
Absolutely. We'll be looking at carbon isotope ratios. You know, we know that a fair bit of organic material in the form of micrometeorites and so on falls onto the surface of Mars. And, you know, from the carbon that we've seen in the atmosphere, it's heavy. We would expect, in fact, we know that much of the stuff that falls on Earth is much lighter than that. And so what we'll be trying to do is, if we have enough organic compounds, directly look at their isotope ratios. What we've brought along with us to Mars, but we've not exercised yet, is a tank of oxygen. And that's exactly what we intend to do with the oxygen, is if we have very refractory organic compounds that are not producing a range of distinct species, what we can do is just turn them all into CO2 by oxidation at high temperatures in one of our cups, and then we look at the isotope ratios. So there's a variety of methods that we have for looking at organics, and isotopes is certainly one of our prime methods of trying to understand where they came from.
Thanks. I'm Irene Klotz with Reuters and Discovery Channel. John, could you put this discovery in context with the issue of Mars habitability as a whole? In other words, if you hadn't found this, would it have impacted that sort of future searches at Mount Sharp one way or another, or the fact that you have found what you found so far do anything to kind of put one plank in this long ladder? Thanks.
Yeah, I think that's actually the way I would describe it. You know, we're working on a mission that is, it's always going to be difficult to describe in a very general way what it is that we're discovering. And you know, we do want to be very careful about each step along the way. So in this particular case, let's go back to what it is that we're basically trying to do. The MSL is a mission that undertakes the search for habitable environments. And there's three ingredients that are necessary for that. One is that you need a source of water. All microorganisms need water. The second is you need a source of energy in order for them to do metabolic processes. And the third thing is that you need a source of carbon, which is an essential building block for biological structures. What tends to happen is that there's a lot of attention paid to the third of those things. And, you know, this week we had an exciting report in the planetary community about the discovery of organics on Mercury. You know, this shows that this essential building block is not uncommon in the solar system. It's actually kind of surprising to us, you know, that, and the thing we're digging into with the soil is to look in there to see if we could actually find anything. And I think if we would have found something that would have been so abundant that Paul wouldn't have had, we would go through the process of trying to eliminate the other things, that would have actually been a surprise to us. And the reason why is to come back to the issue of the energy source for the microbes. So when you look at the soil, you see a bunch of chemicals in there. A lot of these compounds are oxidized components. Some of them, very interestingly, seem to be reduced components. So that tells us that both of these things may exist together in the soil deposit, but by understanding the chemical composition, it allows us to consider which of those things might have been necessary ingredients, what chemical elements are present in those that would be essential building blocks for life. So we've ticked off the box, as Michael said. Water, got it. We just got it again in the form of some of these compounds that Paul was talking about today. These are hydrated compounds. Now we're working on the chemistry part, and we're still looking for organics. So we're actually a step ahead of where we were beyond the conglomerate and the simple water discovery.
Okay, we'll take another question from the internet.
These are from Kelly Beatty of Sky and Telescope, a two-part question. One, given the strong UV at the Martian surface, is the chlorinated methane a byproduct of methane destruction? Or if it's indigenous, what is its destruction lifetime? And then the second part is, could you please discuss the significance of a D to H ratio that is 5 times that on Earth and that varies seasonally? What are its possible sources?
So in answer to the first question, I think it's very likely that the chlorinated compounds that we saw, chloromethane, dichloromethane, and trichloromethane, were actually produced as this perchlorate broke up, and some very reactive chlorine was released, and then that reacted with carbon. And the thing we have to untangle is what form of carbon was that reacting with it? Was it some of the carbon, some of the CO2 that was being released also at the same time, or was it from some other source of carbon? I kind of doubt if it had anything to do with ultraviolet radiation processing, but don't know. That's a good question and something to look at. The significance of the deuterium to hydrogen is, it's one of those ratios that's just way, way different than terrestrial deuterium to hydrogen. And that's because it's so light. When water dissociates, that's where ultraviolet radiation does come in. The water in the atmosphere will break up, it'll form hydrogen, and then some of the lighter part of that hydrogen will more rapidly escape to space than the heavy hydrogen. So you imagine that over Mars seasons, over Mars obliquity cycles, where the polar caps might be moving around and so on the average, that ratio just keeps going up and up with time. What's going to be really interesting again is if we can find some very, very old trapped water, for example, in a high temperature hydrated mineral where the water is not released to very high temperatures, and if that was formed very early, perhaps when these layers at the base of Gale Crater were forming, if that water has a much lower deuterium to hydrogen ratio, then that's really a good reference point. That's what we can tie some of our models to of how the atmosphere might be escaping. So this is just one data point. We don't know that it's an average current Martian D to H ratio. We'll be making more measurements of the atmosphere. We'll be making more measurements of sand and dust, and we'll see what answers we get. But it's one point of current Mars that we're trying to pin down, and then we'll be looking for these same ratios in old Martian rocks as well.
Paul, isn't one of the implications is that from modeling, then you can figure out how much atmosphere you used to have?
Yeah, that's absolutely one of the ideas, both of this mission and the next mission, MAVEN. You understand with the MAVEN mission that's coming up what the current rate of loss of the atmosphere is, and then you make a model, you predict as best you can, back billions of years, how heavy the atmosphere might have been. Was it more similar to the Earth's atmosphere? Was it a little bit less? Was it a lot less? That really ties to how long surface water might stay there and where you might have a nice little environmental niche that's warm enough for microbial life to form. But a real interesting data point that we don't have yet from measurements in situ, although some measurements have certainly been made on Martian meteorites, is what the very, very, very old water looks like. And we're looking forward to carrying out the search for that very old water and looking at its deuterium to hydrogen ratio.
Hi there, Dan Simon with CNN. I wanted to ask you a question about photographs because I think people really love seeing them. For instance, the one on the screen right now. I'm wondering what you've learned from the photos, and if you could just give us a little insight in terms of how they're beamed back to Earth, what the process is, how you process them, how long it takes to see them, et cetera.
Okay. How they get back to Earth is just radio, right? The magic of electromagnetic radiation. The rover has, 17 total cameras, and the MAHLI, the Mars Hand Lens Imager that made this mosaic, that's 55 individual images mosaic together, is just one of those cameras. 4 of these cameras, the MAHLI and 2 mass cams and the descent imager that took pictures as we were landing, actually acquire the images with a color CCD, right? Just like you would have in your iPhone or camera or your point and shoot. So those pictures actually come back already in color. For the Mars Hand Lens Imager, the MAHLI, these pictures here went out to the public on the internet on JPL's, Curiosities raw image website faster than I could even see them, to just go right out. Okay, so and the processing on those raw images is none. So you can actually go to that website and see what these things look like. It's like if you took your own camera to Mars and took a picture. Now, one can do processing. In this case here, this is mosaic together, so you had to stitch all those pieces together. And I'm sure that we did some stretching to sort of bring out the detail, but it's actually kind of hard to stretch this because the rover is so white and so bright and the dirt is so dark. So,
Ken, another point is that these things don't come directly to Earth. They go up to an orbiting satellite, and then they come down. So we're always trying to figure out, whose data comes down first, and the imaging certainly takes up big hunks of data.
That's a good point, yeah. Did I cover that?
Okay. Go ahead, Rick. Oh, okay.
Thank you. For those of us who are not quite chemists, if I'm understanding this correctly, if the chlorine compounds, carbonated chlorine compounds, are made from carbon released from the rocks in carbon dioxide reacting with the chlorine, then basically all you've found is carbonates, which you already knew existed, correct? This would be exciting if it comes from a different source?
Yeah, I mean, what would be very informative would be if we had had a whole suite of organic compounds. If we take a Murchison meteorite, for example, or if we take microbes that are living in some even extreme environment on Earth that aren't very abundant, and we do this same type of experiment, we see a whole suite of organic structures produced. We see aromatic compounds and so on. And what we're seeing here is just some very simple compounds, and it's entirely possible that they're coming from the chlorine that is released, very reactive chlorine that's released, and picking up carbon from somewhere. We have to try and understand where that carbon is coming from. But the informative thing in really understanding a source of carbon, what we would have to have would be a whole variety of compounds. For example, the stuff that comes in from space is processed by radiation in space, and so the structures of the organic compounds reflect that. They're kind of randomized. You don't have long linear chains that enzymes make on Earth when biology's at work and so on. So if we're ever to find an environment where we see lots of organics, then we're really onto something. We can really make some conclusions, or hopefully make some conclusions about where the organics came from. But if we just see these traces of very simple organic compounds, it's much more difficult to draw conclusions.
Hello, my name is Radu Yakov from CuriosityOnMars.com. This is a question for Mr. Paul Mahaffy. Regarding the SAM material analysis, if we are looking at the high runner materials on both the solid materials and for the gases, we can see that we have compounds specific to clay and the calcium oxide, which is 7%, very high runner, the third high runner. And on the gases, gases, we have H2O, the water, and CO2. And I was wondering, could this come from calcium carbonate, which on Earth we know it's making most of the limestone?
Yeah, that's a great question. I think I understood at least the last part of it. Does the CO2 potentially come from calcium carbonate? The answer is no, we don't think so. And the reason is that we don't do mineralogy nearly as good as Chemin does. And however, we can detect very trace amounts of things like carbonates. But one thing we can do with carbonates is we can look at the temperature that the CO2 evolves. And even the highest temperature component of the CO2 that we see is not high enough to be calcium carbonate. So we certainly believe this is not calcium carbonate. It's possible that it may be from a magnesium or iron carbonate, but not from a calcium carbonate.
Yeah, this is Dave Perlman from the San Francisco Chronicle. For Paul Mahaffy, do either SAM or ChemMin have the ability to detect chirality in any of the molecules that you've discovered or found so far? And if not, how crucial would that be if you were able to detect the chirality and find something that was obviously different from that on Earth?
Yeah, the question was, can we detect chirality in any of the compounds that we've found so far? The answer is no, certainly not with these compounds. The focus of SAM was really to do kind of a broad chemical survey, try and understand the breadth of the chemicals that were there. We do have one column that for a specific kind of compound for nitriles, if there was a suite of compounds present and these particular compounds were there, there's a bit of an outside chance that we might be able to get at chirality. But that's certainly not the focus of the experiment. Some of our wet chemistry, we're focusing on these interesting compounds that are important for life, like amino acids and so on, the things that make up proteins and nucleobases and so on. But we've not exercised the wet chemistry yet, and we're going to hold off on that really till we find a site that we think is really interesting, really rich in organics, and that would be a good opportunity to try and get at some of the breadth of the organic compounds there. But we do not really have a good capability on SAM to detect chirality in a range of molecules.
Okay, another question from the internet.
This one's from Tim Olson with Earth Magazine. What's on tap for the upcoming stops at Point Lake, Yellowknife, or beyond as far as scooping up more soils and testing again for organics, DH, chemistry, and other soil signals?
Yeah, so the rover now is parked at Point Lake, and we're finishing up there, and we're doing a survey as we go down into the area we call Yellowknife Bay. And we're going to stop at least one other outcrop that we've called Shaler. It has a different expression. It looks like something that has a much more finely layered aspect to it than anything we've seen so far. And we're going to work our way down in there. We're going to guess probably this should happen in the next couple of weeks. We're probably going to do imaging as we drive by these locations. We'll certainly use ChemCam. We may or may not get the arm out and do contact science, because we really would like to try to find a target for drilling that we can begin to start working on before the holidays start. So that's sort of our tentative schedule, but it's nothing firm so far.
Okay, well, that's it for our formal Q&A. You're welcome to stay for just a few minutes and ask questions of the panelists directly. We have to be out of this room by 10:30, so we're going to be ushering people out as soon as we get close to that time. I'd also like to tell you that our next press conference will be at 11:30 a.m. It's about climate and civilization. It will take place in the usual AGU press conference room, which is room 3000 in Moscone West. And all press conferences from now on will be in that room. And just for anyone who's checking out the press conferences online, all of our press conferences also will be web streamed. So thank you very much.